I'm going to try to get you some visualizations about how graphs of a function, the first derivative of that function, and the second derivative of that function are all related. Hopefully you realize we're not just talking about graphs named f. That's the common thing. This could be the graph of g, g prime, and g double prime. So by the end of this, hopefully you'll be able to find and justify local extreme values, meaning a relative minimum, and a relative minimum or a relative maximum. And we have two tests for that. The first derivative test, which you're going to be shocked means we'll use the first derivative. And the second derivative test, you actually might be shocked, where we use the second derivative along with the first derivative. Okay. We're going to also find intervals where functions increase or decrease. And we're going to find out about concavity and what that means in terms of graphs. So, what must be true about the first derivative of a function at an interior point of the domain in order for the original function to have a local minimum at that point? What the heck do I mean? So here is some function, and we're talking about a local maximum. So let's choose this place right here, a local maximum. And we want to know something about the first derivative of this function. I don't mean the first derivative of the equation. I mean information we know about the first derivative. What you should be able to tell is that for the points just to the left of that maximum, the first derivative is positive. This graph is increasing. The graph would have tangent slopes that are positive. To the right of that maximum, the slopes of this graph would be negative. The derivative of this graph would be negative. Is that true at this other local maximum on the left, that the slopes change from positive to negative, that the derivative changes from positive to negative? Yes, that is true. Could that happen in another way without a nice, smooth, continuous function? It can. So let's think of a graph that has a cusp. What's happening to the left of that cusp, the left of this local maximum? The derivatives, the slopes of the tangent lines, are positive. And right after, to the right of that local maximum, the slopes of those tangent lines are negative. That idea is the first derivative test. If the first derivative changes from positive to negative, and that function is continuous, you have found a place where that function has a local maximum. So what about a local minimum? Well, let's think about that. If we're looking for a local minimum down here, what are you looking for in terms of the first derivative? Well, we're always looking for continuity, so h must be continuous, and at this place, h prime, the derivative of h, changes from negative to positive, because we can see that the slopes to the left of the minimum are negative, and the slopes to the right of the minimum of h are positive. So here's what we're going to do. We're going to make sure a function's continuous. If a function wasn't continuous at a point, it couldn't have a minimum or maximum at that point. We're going to find the first derivative of the function. We're going to find critical values where that first derivative is equal to 0 or undefined. And we're going to test intervals to see if the first derivative changes sign. That's what we're looking for, a change in sign of the first derivative. The reason I say justify, very excitedly with an exclamation, that's the most important part. And it ends up being a lot of words, but you're going to keep using the same words over and over, so eventually you'll be pretty confident. Before you start, you should have a guess as to what x cubed minus 12x minus 5 looks like, something like this. The left and right hand end behaviors go in different directions. Maybe this graph has one maximum and one minimum. We're not sure. So let's find out. We're going to use the first derivative to figure out what's going on. So we're given a polynomial. Polynomials are continuous and differentiable everywhere. So maybe we want to say that. That y equals x cubed minus 12x minus 5 is continuous. Okay, so y prime is equal to 3x squared minus 12. That's the whole thing. So we're looking for critical values because that's the only place a derivative could change signs. Where is 3x minus 12 going to change signs? Only where it's equal to 0, where 3x minus 12 crosses over the x-axis. Don't forget, critical values are also where a derivative is undefined. But since we're talking about a polynomial, y prime is never undefined. Okay, so 0 equals 3x minus 12. 0 is equal to 3x squared. 3 times the quantity x minus 2 times the quantity x plus 2. Which means x equals 0 is nothing. X equals 2 and x equals negative 2 are the two places where the graph we're looking at has horizontal tangents. Ooh, I'm going to need to erase this. So I don't know much about this graph, but I do know a little bit more. I don't know what the x-axis is or something like that. But right here, this occurs at negative 2, and right here, this occurs at positive 2. We found out that y prime was equal to 0 at negative 2 and positive 2. So hopefully, we'll find out that this graph has a local maximum at negative 2 and a local minimum at positive 2. The next thing we're going to do is make a sign chart. Let's do it in a different color so we can see we're doing something different. And a sign chart contains all critical values and places where a graph is undefined. So our sign chart is only going to contain negative 2 and 2. We're going to include that the inputs to this sign chart are x's and the output is the sign of y prime. If y prime can only change signs at 2 and negative 2, all we have to do is test intervals. So we're all going to test x equals 0 first, and we're putting these numbers into y prime is equal to 3x squared minus 12. Or it's probably easier to think of the factored form, because all we're thinking about is positive and negative. So if I use 0, we don't really care about 3. 3 is always positive. 0 minus 2 is negative. 0 plus 2 is positive. So a positive times a negative times a positive is negative. We'll write a negative sign in between negative 2 and 2. You should be confident that y prime is negative all the way between negative 2 and 2, which notice on the graph over here, it does appear, like I previously said was going to happen, everywhere between negative 2 and 2, y prime is negative, or you could say y prime is decreasing. Oh no, I lost my graph. Okay. Okay, so let's choose a number larger than 2. I'm not going to choose 3. I'm going to choose like 1 million, because 3 times a million minus 2 times a million plus 2 is definitely going to be positive. And choose a number smaller than negative 2, like negative a million. 3 times negative a million minus 2 times negative a million plus 2 is basically a giant positive number. That's all we care about. I like to teach my students that underneath a sign chart for the first derivative, draw increasing and decreasing sorts of things. So, like this. Because I had a positive, I drew increasing, and this sort of represents approximately what the original graph, x cubed minus 12x minus 5 looks like. So, I actually have to justify, that's the most important part, which is just explaining what's going on this sign chart. And hopefully you can tell, we're going to talk about x cubed minus 12x minus 5 has a local maximum at x equals negative 2. X cubed minus 12x minus 5 has a local minimum at 2. We're going to start off with the most important thing, and that is y equals x cubed minus 12x minus 5 is continuous. The function isn't going to have a maximum or a minimum where that function doesn't exist. So what do we see? We see that y prime changes from positive to negative at x equals negative 2. So y equals x cubed minus 12x minus 5 has a local minimum. Nope, that's not true. Has a local maximum at x equals negative 2. That does sound redundant, but you need to say what happens, meaning y prime changes from positive to negative at negative 2, and you need to say the consequence. So the original function has a local maximum also at negative 2. Why do we need to say both? Let's try to contrast that with y prime changes from positive to negative at negative 2. So y equals x cubed minus 12x minus 5 has a local maximum without anything else. That implies somewhere, but not necessarily at negative 2. So let's put that back in. Okay. Let's make another statement about the local minimum. What am I going to write? Y prime changes from, what does y prime change from? From negative to positive at x equals 2. So y equals x cubed minus 12x minus 5 has a local minimum at x equals 2. That's it. That's the first derivative test, using the first derivative and looking for a change in sign of the first derivative. Let's try that again. Do you know what negative x to the fourth looks like? It's something like this, definitely opening downwards. Because it doesn't have an x cubed or x squared term, I happen to know that negative x to the fourth only has one turning around point. I'm expecting only to find a local maximum. What do we do first? Always we check for continuity. And since negative x to the fourth is a polynomial, we know it's continuous and differentiable everywhere. Cool. So let's find y prime. That's easy, negative 4x cubed. We need to find critical values. That's the only place that a function can have a maximum or minimum. So let's let y prime equal 0. And we also know, since we're talking about a polynomial, y prime is never undefined. So we don't need to look for those critical values where y prime is undefined. 0 equals negative 4x cubed, and x is equal to 0. So we only get one critical value at x equals 0, which is what we expect if I could draw correctly. And what is the sign chart going to look like? Well, hopefully we see that y prime changes from positive to negative at x equals 0, because you can see the slopes of the tangents over here are positive to the left of 0 and negative to the right of 0. Let's make sure that's true. Our job in AP Calculus is to show what we know. So I'll change colors again. We'll make a sign chart. These are x values, and we're looking at the sign of y prime. And what numbers do we put on this sign chart? All the critical values, which includes 0 and nothing else. And so what that means is y prime can only change signs at 0. Let's see, what do we get? Well, any number greater than 0, when you put it into negative 4x cubed, well, that's going to be a negative 4 times 3 positive numbers is negative, which means y prime is negative, y is decreasing for values greater than 0. Choose a number less than 0, like negative 1. Negative 4 times negative 1 cubed is positive, which means y prime is positive for all numbers less than 0, and y is increasing for all values less than 0, which matches up with this graph I drew earlier, which isn't a great graph. Let's call it a sketch instead. Okay. So we found, like I expected and you will in the future, that negative x to the fourth has just a local maximum. What do we start off with in our justification? Y equals negative x to the fourth is continuous. You could also say y equals negative x to the fourth is a polynomial, so it's continuous and differentiable everywhere. Okay, so we're going to talk about, do you remember, is this a local maximum or minimum? Local maximum. Y prime changes from positive to negative at x equals 0. That's not enough. That's just a reason. So what do we know? So y equals negative x to the fourth power has a local maximum at that same spot. So at x equals 0. One more example, and let's do an example. You may not exactly know what the shape looks like. You might, if you know what x to the 2/3 power looks like, and you know what sort of transformation has been applied. That's okay. What you should be certain about is squaring and cube roots have domains of all real numbers, so this thing is definitely a continuous function. So what is y prime? Well, we can use the power rule. So 2/3 of the input to the negative 1/3 power. The input is x minus 1. Chain rule, just multiplied by 1. So let's rearrange that actually. We're not ready to set y prime equal to 0. You'll see why in a second. Y prime is 2 divided by 3 times the cube root of x minus 1. Can you tell where y prime is equal to 0? Nowhere. Y prime would be equal to 0 when its numerator is equal to 0. So let's let y prime be undefined. And just tell whoever's reading our work, we already know y prime does not equal 0 anywhere. That way they don't think we forgot. So when is y prime undefined? When y prime's denominator is 0. And hopefully you can do that in your head. That's when x equals 1. So let's make a sign chart. What numbers should we include? We're going to include 1, and that's all. These are x values, and this sign chart tells us the sign of y prime. So we need to choose a value greater than 1 to substitute into y prime. Hopefully you can tell, no matter what number you use, we're going to get the cube root of a positive number inside of there, so the whole y prime is going to be positive, which means y is going to be increasing for x values greater than 1. Choose an x value less than 1, like 0, and you have 2 over 3 times the cube root of negative 1. That's going to be negative overall, which means y is decreasing for numbers less than 1. So does x minus 1 to the 2/3 power have a local minimum or local maximum at x equals 1? A local minimum. Let's write our justification. Y equals x minus 1 to the 2/3 power is continuous. What did we find out based on the sign chart? Y prime changes from negative to positive, where? At x equals 1, so y equals x minus 1 to the power 2/3 has a local minimum at x equals 1. I'm going to stop there with the first derivative test because I know the next part is about concavity, and that's a whole separate topic.